So right now we just focus on capital N is equal to R1, R2, R3. And later on, after you understand this, then we can generalize to M integer product instead of just 3 as shown in equation 75. So based on the assumption that capital N is expressed in terms of the 3 integer product R1, R2, R3, and based on the previous formula that we developed, now we say the small index n can be expressed in terms of n0, n1, n2 as shown in equation 76. By the way, if you remember in the previous chapter, when we consider capital N is the product of only R1 times R2, at that time equation 76 looked very similar to what you see in here, except the equation looks shorter at that time. So equation 76 and equation 77 that you have corresponding to the situation where n equal to the product of the 3 integers R1, R2, R3 is very similar to what we discussed before. Okay. Now, if you look at those equation 76 and equation 77, we recognize that R1, R2, R3 are known. Okay, R1, R2, R3 are known. Now, equation 76 and equation 77, if you look at it, you need to know what is the range of value for N0, N1, N2, K0, K1, and K2. And the value for those parameters are given by equation 78 for N0, N1, N2, and equation 79 for K0, K1, K2. Like for example, the value of N0 will go from 0, 1, 2 up to R1 minus 1. Remember, R1 is known. Similarly, the value for N1 could be anywhere from 0, 1 up to R2 minus 1. The value for N2 could go from 0, 1 up to R3 minus 1. And again, the value for K0 can go from 0, 1 up to R3 minus 1. Notice, N0 go up to R1 minus 1, but K0 go from 0, 1 up to R3 minus 1, not R1 minus 1. So those are equations 78 and 79, which give you the range of value that you can have for N0, N1, N2, and K0, K1, K2. Now, based on that, then the story becomes very similar to what we have been saying many times. Remember, we have the unknown vector C tilde n is equal to summation on the index k f of k multiplied with w raised to the power nk. That formula that I just wrote down over there in red color was come from the informal development of the fast Fourier transform that I talked and explained to you many chapters ago. Now, basically, we make use that same equation that I showed you in the red color. The only thing different is the small index n. Now, you express in terms of the 3 index n2, n1, n0. And keep in mind the relationship between the small index n in terms of n0, n1, n2 are given in the previous slide. So for example, if you look at the previous slide, you can see the small index n expressed in terms of the index n0, n1, n2. You see? And that is exactly what we have done here. So the small index n we express in terms of the index n2, n1, n0. Similarly, the summation on k, the index small k, now is expressed by 3 summation based on the index k0, k1, k2. Same thing, the periodic function f at the discretized time k, now that k is also expressed in terms of the index k2, k1, k0. And then finally, w raised to the power n, small n, now that small n will be replaced by this first parenthesis that I show you in equation 80. And the small index k now is shown you as a second parenthesis, as shown in equation 80 with the green color. So now this is what you got, equation 80. Now with this equation 80, the next thing, just like in the previous chapter, we say let us pay attention to w raised to that power. Let's pay attention to that term. Well, that term is shown right here on the left of equation 81. Now w is here, as you can see on the right side of equation 81. The power p that you have actually is corresponding to this power right here that you see on equation 81, which again come from equation 80. The next thing that we want to do is we want to consider the first parenthesis in equation 81 that I show you in this blue bracket right there. Take the first parenthesis, multiply that with the first term in the second parenthesis. When you do that, you will get this term that I show you right here in blue color of equation 82. Similarly, when you look at equation 81, if you take the first parenthesis, multiply with the second term of the second parenthesis in green color, you will get this term right here, as I show you in green color in equation 82. And finally, if you take the first parenthesis, you multiply with the third or the last term of the second parenthesis in black color, equation 81, you will see that term right there as I show you in the black color of equation 82. So now you can see very clearly the right hand side of equation 82 can be expressed in the form of w raised to the power p1, where p1 represents the power of the first term, as I show you in the blue color. Multiply that with w raised to the power p2, you see equation 83, where p2 is shown in the green power, and multiply with w raised to the power p3, as you can see in equation 83, where the p3, that term, can be seen as indicated in the black color power in equation 82. So equation 82 can be represented using the simple notation W raised to the power P1 times W P2 times W raised to the power P3. So in the next few slides, we will try to figure out what is WP1, what is WP2, and what is W raised to the power P3. Okay, so in equation 84, we just show you how to